Welcome to my mastery assignment for Module 2, and today we will be covering two topics, and the first topic is area between curves. Through the fundamental theorem of calculus, this process of integration is just reverse of the process of differentiation. The first part of this theorem is that the integral from a to b of f of x dx equals the inner derivative of b minus a. The second part is that the derivative of the integral from a to x of f of t equals f of x. Here's a case in which it makes it easier to visualize how area between curves work. Here I drew the graph, and that shaded area is what you're looking for, and we can determine that f of x is greater than or equal to g of x, and from this we conclude that our area will be the integral from a to b f of x minus gx dx, and this is basically the top function minus the bottom function. Here is another case, except the graph is in terms of y. As you can see here, f of y is the outer function and g of y is the inner function. Here's an example in which you will determine the area of the region enclosed by y equals x squared and y equals the square root of x. First thing you're going to do is graph. It's very important so you don't get confused, and that is the region you will find. We will now use the area formula that we saw in the previous example. Now we can set up our integral, but first we will find the intersections to get our limits of integration. You can do this by finding it in the calculator or setting the problems equal to one another. And now the integral you will have is the integral from 0 to 1, the square root of x minus x squared dx. And now you antiderive to get 2/3 x to the 3/2 minus x to the 3rd power over 3, and you evaluate that from 0 to 1, and then your final answer is 1/3. The next topic we will cover are volumes using cross-section. A cross-section of a three-dimensional region in a space is the two-dimensional intersection of a plane with a region. Here's an example with a function that has circular cross-sections, and this circle has cross-sections in the shape of squares. The volume of a region in a space with an integral cross-section area a of x for the interval a to b is given by volume equals the integral from a to b a of x dx. Here are the formulas for cross-sectional areas. It may be helpful to memorize or write these down somewhere. Here's an example in which you will compute the volume formed by f of x equals x squared minus 3 and g of x equals 5 minus x squared. The cross-sections are squares. Here is what a function with the cross-sections that are squares would look like. The first thing you will do is graph everything so you do not confuse as to which function is larger. And as you can see here, g of x is larger than f of x. And the formula you will use is s squared, since the cross sections are squares. Now you will use that formula to get your cross-sectional formula, which is g of x minus f of x, and everything is squared. And then you will plug in your functions and then simplify to get 8 minus 2x squared, and everything is squared. Now you can set up the integral to find the volume, and first you will find your intersections, and you can do this through the calculator or setting the functions equal to one another to get -2 and 2. Then you will have the integral from -2 to 2 of 8 minus 2x squared, everything squared, dx, and that'll equal 832 over 3, which is approximately 277.333. I hope you learned a lot and thanks for watching.